All right, good afternoon, everyone. Let's get started. So today we're going to talk about EfficientML.ai Lecture 9, Knowledge Distillation. So this is a new chapter after we have talked about pruning, quantization, neural architecture search. Now it's another technique about knowledge distillation. So make sure you have finished the homework 1 and already working on lab 2, and just a reminder. So today we'll learn about knowledge distillation, which is an orthogonal technique compared with pruning and quantization. We'll talk about what is knowledge distillation, what is teacher model, what is the student model, and also how do you match the logistics or the weights or the activations or the gradients, whatever, how to match teacher and student. We'll also talk about self and online distillation, and also distillation for different tasks. And finally, we'll talk about another technique, network augmentation. Okay, so let's get started. So what's the motivation here? Again, we have limited hardware resources across different platforms. In the cloud, GPUs are super expensive, and the memory capacity is also limited, 80 gigabyte, 120, 8 gigabyte, etc. Not to mention the mobile devices, microcontrollers, you have a couple of hundred kilobytes of memory versus tons of gigabytes of memory. So compare with the neural network on the GPUs, we can run ResNet, we can run VIT, TinyML, we can run MCUNet, MobileNet V2 Tiny. So the question is, how do we train these tiny models that can fit very little memory budget, or even comparable, or even match the accuracy of those larger models? So that's for TinyML, and even for the cloud use case, even for the cloud AI, these days large language models are getting super big, and we want to reduce the serving cost. Therefore, even on the cloud, knowledge distillation makes a lot of sense. Can we distill a 7 billion parameter model to a 7 billion parameter model, right? So we can save 10x the memory traffic for the weights. So that's the question we want to answer. Can we use a larger model to guide a smaller model? Okay, so we have a larger model, a teacher model on the left. We have a smaller model, student model on the right. Naively training these models, intuitively we can have very different accuracy, right? 82% versus only 52%, right? And the question is, can we help the training of tiny models with the help of these larger models? Okay, so this image is the illustration of knowledge distillation. Okay, first of all, we share the same input. Okay, the same input is fed to both a larger teacher network and a student network. The teacher network is usually larger, like Llama 270B. Okay? And the student model is usually smaller, like the Llama 2 like 7B. Okay? And then given the input, they both produce some prediction logics. Okay? Logic 1, logic 2. Okay? And when we are training the student network, we usually have some loss, either classification loss. Maybe this is the most popular. So what is new here? We also add a new loss called distillation loss. Okay, distillation loss between teacher's logics and the student logics. Okay, so what we are trying to do here is trying to match the logics of the teacher and the student. Okay, trying to match the teacher with the student. So that's a new loss term we added here. What's the intuition adding this loss? So if you look deeper into the prediction, given the same input image, say a cat here, the teacher network, the two logics, one for the class cat, one for the class dog. The logit for the cat is 5, dog is 1, meaning that it thinks it is a cat. Strongly believe this is a cat. And if we normalize them after softmax, the probability is 98% versus 1.7%. Okay, so the teacher model strongly believes this is a cat. Versus the student network, the logic is 3 and 2. Okay, if you do the softmax, the probability is 73% versus 26%. Okay, the classification is still correct. So we don't have any loss coming from the cross entropy loss. Cross entropy loss is 0 because the prediction is correct. It's a cat. But you can tell their output from the teacher versus the student, they are also quite different. The teacher is more certain this is a cat, so we have a higher probability, versus the student model is less certain, only 70% possibility. Okay, so here we are trying to match the prediction probabilities between the teacher and the student. That's the missing part from the cross entropy loss. So how did we derive this probability? So that is through the softmax function. That's a review of the softmax. Exponent of 5 divided by the exponent 5 plus exponent exp of 1. Right? And similarly, we can calculate the other class. Versus the student model is less confident. So our goal is to bump up the probability for the cat and bump down the probability for the dog to match that of the teacher. So how do we do that? Let's first learn this concept called temperature. Okay? Temperature. So in the softmax, if the temperature is 1, that's our original case. If the temperature is larger, then the output distribution, the probability gets smoother. Rather than 98, 1.7, this is 60%, this is 40.1%. Okay? So a larger temperature will smooth the output probability distribution. So mathematically, where does the temperature T appear? So appear in the denominator of the softmax. Okay? For example, when we apply a temperature of 10, previously exp5, now it becomes exp5 divided by 10. And similarly here on the denominator is divided by 10. So this is the formal definition of knowledge distillation. Okay, so neural networks typically use softmax function to generate the logics to class probabilities, which is for different class with a different temperature, the probability is expz for a particular index divided by the sum of the exp. Okay? And ij ranges from 0 to c minus 1, where you have c classes. And T is the temperature, which is usually set to 1. And the goal of knowledge distillation is to align the class probability distribution between the teacher and the student network. So we are trying to align this probability distribution. So what can we align? Okay, what to match? What tensors can we match? So here we summarize a bunch of ideas where we can match. So primarily, the summary we get. So let's go through them one by one, starting from the output logics. Okay, so we have seen this figure. Not only do we have the classification laws, but also we try to match the logics between the teacher model and the student model. So trying to match the output logics, cat and dog, as the output prediction. Okay, so how do we match them? We can either use the cross entropy loss. We have two distributions, one for the teacher, PT, one for the student, PS. We can also do the simple L2 loss, PT minus PS. So that's very simple, just to match the output logics. Okay. What else can we match? Not only the output, we can also try to match the intermediate tensors, including the intermediate weights and also the intermediate features. Okay, so let's look at them one by one. Here we no longer have the output, matching the output. Now we are matching the intermediate tensors. Okay? So the teacher model, layer 2, this is the student model's layer 2. Okay? So here we try to match the intermediate weights. these two layers, we try to match the weight. What is the challenge here? Matching the weight of the student versus the teacher. Remember the question?
So I guess there are different sizes of models. You need to do some sort of like low rank approximation or compression of the larger model, and that induces another loss.
Yes, you got it. You got it. So difficulty is the teacher model and the student model, their weight dimension is different, right? Teacher model is usually larger. The weight tensor has larger dimension. Student model usually smaller dimension, right? So what we can do here, just like you proposed, we can do a low rank approximation, right? And here we can also do a learner projection, right? Learn a one-by-one conclusion here that can map the student's smaller tensor to a teacher's larger tensor. Okay? So this is the teacher network, which is larger, wider. This is the student model, which is narrower, smaller. Okay? And we try to match them by using this projection matrix, this blue matrix, project from a smaller channel to a larger channel. Okay? We can learn this projection matrix. And then we can match the output of after this projection matrix with the teacher model. Okay? So between the teacher weight and the student weights plus a transformation matrix. So here, the blue part is the transformation matrix, which is just a simple FC layer to align the shape, the dimension of the teacher versus the student weight. Okay, there are also other methods, like you can use low rank to match. We are going to skip that here. We can also match the intermediate features, not only the weights, but also the features, the activations. So previously we were matching the weight. Now we are matching these activations to match the intermediate feature maps between the teacher model and the student model. The intuition is that teacher and student network should have similar feature distribution, not just the very end. That's an extreme case, not just the very end, not just the output probability distribution, but also across all the layer, different places, the feature map should match. So we talk about weight matching, activation matching. What is left? Gradient matching. Okay? So we can also try to match the gradient from the teacher and the student. Let's brainstorm a little bit. They are of different dimension, right? So naively matching the teacher and student gradient may not work. So beyond the weight gradient, there's also the activation gradient, right? During backpropagation, the backpropagation part is usually 2x lower than the forward part because it's doubling the computation. One is computing the weight gradient, the other is computing the activation gradient. If weight gradient is hard to match, can match the activation gradient. In particular, the activation gradient for the very first layer, for the input. Since teacher and student, they are sharing the same input. Right? So this is intermediate attention map, matching the intermediate attention map. We backpropagate the gradient all the way to the input image. Okay? So this is the input image, and this is the gradient when we are backpropagating the gradient from the output all the way to the input. And this is the gradient on the input tensor. So attention of a CA feature map is defined as partial loss over partial x, how is the learning objective, and what does it mean for the input feature map? So if the gradient is large, like here, in the nose, in the eyes, in the face of this box, it means that just a small perturbation in this pixel, in this area, okay, will significantly impact the final output. Meaning that this area is very important, very crucial for us to make a decision what it is. And indeed, it makes sense. At position ij, the attention over there is defined as the gradient with respect to that pixel. And what we are trying to match is this attention map from the teacher versus from the student. They can be easily matched because their dimension is the same. The gradient's dimension is the same as the image. And both the teacher and student are sharing the same image, so we can match them. And let's see, given different networks, what does the gradient look like? So this is, the second row is less than 34, third row is less than 1, they are of the same family. Versus the first row is network in network, that's a different family. We can see that networks of the similar family, the third row and the second row, their gradient is very similar. Well, compared with the first row, the gradient differs a lot, right? Here, these two differs a lot, well, these two are very similar. So attention map of these performant ImageNet models, both above 70%, are indeed similar, but less performant model, this one is only 62%, has quite different feature map. Therefore, when we are doing the distillation, we try to match those intermediate feature maps on DL over DX, trying to match the gradient with respect to the activation. Okay, any questions so far? We talked about matching the weight, matching the feature, matching the gradient, also matching the output. Okay, we can also match the sparsity pattern. Okay, so how do we match sparsity pattern? First of all, where does sparsity come from? So usually we have a random activation function. If we have a random activation function, then there is sparsity. Okay, so we want to match the sparsity pattern after the random activation function. Neuron is activated if it is larger than 0. If it is not activated, then it becomes 0. Right? If it's smaller than 0, it becomes 0. So at every feature map, we try to match the teacher's sparsity pattern versus the student's sparsity pattern. We can also match the relational information. Okay, what does that mean? Previously, we have been looking at each tensor. Okay, the output tensor, the gradient tensor, the weight tensor, etc. Now we want to look at two tensors, not just one tensor, not just match one tensor, but two tensors. For example, this is a teacher, this is a student. The teacher has 32 layers, the student has 14 layers. Okay. They both have 3 stages. The teacher has more residual modules per stage, like 5 in the first stage, versus the student has only 2 in the first stage. Teacher has 5 in the second stage, student have only 2 in the second stage. Each stage have the same resolution, and the different stage will be downsampled by 2 compared with the previous stage. So what we are doing here is that we can, although they have different number of modules, 5 versus 2, they also have different number of channels. The teacher model may have larger channel like 1K. Here we have smaller channel like 512, right? But the relationship between the input of this module and output of this module is only dependent on the number of channels, right? So for example here, we can just calculate the relation between the input and output, which is of dimension Cin times Cout, since we did a reduction on the spatial dimension, okay, for both the teacher and student networks. So we can have a Cin times Cout tensor here for the teacher, and that of the same tensor for the teacher and also for the student. Now we are trying to match the relationship between the input and output for the teacher and input output for the student given a stage. We can also match the relationship not only for the different tensors, but also for different inputs, okay, different samples. Like here we have 3 samples for the bird 1, bird 2, bird 3. Previously, we just try to match the distance between the teacher of bird 1, teacher of bird 1 versus the student of bird 1, versus teacher of bird 2 and the student of bird 2, right? So they are independent. These 3 birds are independent. And now we try to match them jointly, okay? T1, T2, T3 from the teacher versus S1, S2, S3 from the student. They should have very similar relationship between each other. Like here, T2 is on the right of T1, S2 should be on the right of S1. Okay? Versus in this loss, it doesn't care whether S2 is here or within the circle 330 degrees, it doesn't matter. But here it matters. Okay? The relationship matters. So conventional KD focuses on matching the features or matching the logics on just one input. Okay? The relational KD looks at the relation between intermediate features across multiple inputs. Okay? So this is tried on image models. For your homework, for your open-ended projects, feel free to try this on large language models, whether it makes sense to try this relational knowledge distillation across multiple inputs. When you are compressing like large language model or visual language model, maybe this method can shed some light. So this is putting it in math. So we have multiple samples. We calculate the L2 distance between the students. First sample, second sample, first sample, third sample, nth sample, etc. Okay. So altogether, how many terms are there? We have n times n minus 1 divided by 2, since it's pairwise, representing this pairwise distance of feature vectors. So on the bottom, we compare, this is individual knowledge distillation. Okay? We just pair the distance between T1 and S1, T for teacher, S for student, T2 and S2, Tn and Sn, right? Now we not only care them independently, but we care the relationship between among them, right? So we have to calculate, given a tensor, we want to go back to visit the distance with all the previous input samples. So that's the difference between the relation within the model calculated separately for each input versus calculating the relation across different input samples. Okay, so that's all for the second part. What to match? Match the gradient, match the weight, match the activation, match the logics, match across different input samples. Okay? So for that part, we have one teacher and one student. We require 2 models. What's the problem for that? Especially when the scale is larger. You have to first train a very big model, very giant model. You have to first have a teacher before you can have a student. Right? But training this teacher could be very expensive. Like training a llama, 70 billion parameter llama is pretty costly, right? Then if we don't have the teacher, how do we apply knowledge distillation to begin with? So that's what we try to answer in the third part of the lecture. Self and online distillation. Just like self-learning. We don't have a teacher. You just learn by yourself or learn together with your classmates. Okay? And for the previous distillation, we have to train it once. Okay? First, finish the whole training process, get a high performance teacher model, and then start this distillation process for the student model. But now we just want to do it only once. Just do it only once. Online distillation. You distill while you learn. Okay, so that's the opening, the motivation for the third part, self and online distillation. And let's see how that works. Starting with self distillation. So teacher model, like we mentioned, is usually larger than the student model, and that is fixed, right? We have a large fixed teacher model and a small student model. The disadvantage of a fixed large teacher model has some disadvantages since you have to train it, which is very expensive to train. And does it have to be the case we have a fixed large model in KD? Actually, not necessarily. It can be of the same size. It doesn't have to be a fixed size, fixed large size. So this project called Born Again network, and this iterative training stage, okay, using both the classification objective and also the distillation objective. So what is interesting here is that the teacher and student model size, the architecture is exactly the same. Same architecture, same model size. Not bigger teacher, small student, they're the same size. Okay? So what it does here is we first train step 0 using only the classification cross entropy loss to train the teacher. And in the second step, we use the cross entropy loss to train the student. And also try to match the logics from the teacher from the previous step versus the student from the next step. And on and so on. Each step, we match, we try to train it with the cross entropy loss versus the distillation loss with the previous step. We use the previous step here as a teacher to guide the next step. And as a result, the student S1, S2, SK, S1, S2, SK is getting better and better. When the training finishes in the last step, since these architectures are the same, we can ensemble the prediction together. Okay, we can ensemble these output together to get the final output. To ensemble this output to get even better performance. So that's the interesting part, where the teacher and student, they are of the same size. We can also do online distillation. Okay, online distillation is saying that we have two networks, they can be the same size. Okay? Not necessarily the teacher is larger than the student. They can be the same, and they are trained from scratch, rather than we first train the teacher model. After that trained, we do the distillation. Now we don't have a teacher, we don't have a student. Everybody is just starting from scratch. Just like in the classroom, only you and your neighbor, your classmate. And you sit together. Network 1 is the teacher of network 2 when we are training network 2. And network 2 is the teacher of network 1 when we are training network 1. Okay, so they are acting as the teacher of each other, which is the interesting part. So just like you have two models, they are of the very exactly the same size. What you do here is to add the loss, not only the cross entropy loss, so here S for student, T for teacher. You have the cross entropy loss for the student, Y is the ground truth label, and then you have the KL divergence, the KD loss, knowledge distillation loss, treating the second model as the teacher, first model as the student. When you're training the teacher, you not only have this cross entropy loss, but we use the student model as the teacher and the teacher model as the student. Okay, so learning from each other. So the interesting part is that it's not necessary to pre-train this teacher and student. Okay, this teacher. The teacher can be initialized, trained from scratch together with the student. And the student can be the same size as the teacher. You not necessarily need to have a larger teacher, which is the interesting part here. Okay, so here, when we are training P1, P2 is the teacher. When we are training P2, P1 is the teacher. So people call it deep mutual learning. And we can see here on CIFAR 10, CIFAR 100 data set, the deep mutual learning can improve both the student and the teacher modules. Okay, so the DML in the middle row is showing the performance after this online distillation compared with independent training. Okay, and we can also have a combined approach. Okay, combined approach to combine the online distillation and also combine the self-distillation. Okay, so here the title is Be Your Own Teacher. We don't have a separate teacher. We don't have to train the teacher from scratch. Have a pre-trained teacher model to guide the student model, but we can train from scratch using this deep supervision plus distillation. Okay. So we are using the deeper layers output as the teacher to distill the information for shallower layers. So the teacher and the student no longer comes from two different models, one large model, one small model, but they're coming from the same model, but different places. Those deeper layers output will be the teacher for the shallower layer. So that's the beauty of this project, where you don't have to maintain two copies of the weight. You just have one copy of the weight. Otherwise, you have to double the GPU memory, which is expensive. You only have one copy of the weight. And the teacher is very simple. It's just a deeper layer to supervise those shallower layers. And the intuition is that the labels at a later stage are more reliable. So the author used them to supervise the predictions for the previous stages. So no teacher, you is your own teacher, but just using the shallower layer, using the deeper layer to supervise the shallower layer. And let's see how that works. So the first row is the baseline. If we use the predictions from the intermediate classifiers, sometimes actually outperform the baseline, which is quite interesting. And this inference efficiency can be improved because we don't have to wait until we go to the last stage. Maybe we can exit early when the confidence is high enough. Okay, so that's all for the first three parts. We'll take a break before we talk about distillation for different tasks and talk about network augmentation. All right, welcome back. So let's continue to talk about knowledge distillation. Now we want to apply knowledge distillation to different tasks to solve real-world problems. So let's start with object detection. So what is object detection? Try to find the bounding box for different objects. You not only want to give the class what it is, but also to tell me where is the object, giving the bounding box for the location. Okay? So we can see the distillation pipeline is more complicated here, but still it includes the basic components, including the trying to match the feature, trying to match the feature map. Here we can use a one-by-one convolution to match the shape, just like we discussed before. The teacher model versus the student model, they may have different dimensions. So we use this one-by-one convolution to match the dimension so that we can subtract the tensor of the same sizes. What is new here? We use a weighted, okay, so weighted P log P here to differentiate the background versus the foreground, right? So the cross entropy loss previously we have is just the P teacher log P student. Okay, what is new here? We added a class condition here to have different weights for the foreground and for the background. For the background, we can allow some difference, but for the foreground, we really want it to be accurate. For the background, we can allow some certain amount of mismatch. So that's why we have a weight here to differentiate the foreground versus the background classes. The next part, we also want to predict a bounding box. Okay, it's not just a class, but it's a location. Okay, x1 by 1, x2 by 2, given those colors into a bounding box. So what's new here, you can see there is an if branch. Okay? So Y is the ground truth, RS is the prediction from the student, and we try to minimize this difference between the student versus the ground truth. Versus here, if the student, the error from the student is larger than the teacher, then we apply this loss. Otherwise, if the teacher is not as good as the student, it doesn't make sense to be a teacher, right? So at that time, we assume the distillation loss to be 0. Okay, so this is very interesting. We add an M term, which is a buffer. Okay, so make sure the loss from the student, the error from the student is larger than the teacher. The teacher is having a smaller error compared with the student plus a threshold. Okay, then it can act as a teacher. Otherwise, we just put the distillation loss to be 0. Make sure the quality of the student is within a threshold within of the teacher. So there is another way to guide the bounding box prediction. Okay, it used to be a regression problem because the XY location for the object is continuous. We can also convert it into a classification problem. Let's brainstorm how do we convert that into a classification problem. We can chunk the y-axis and x-axis into several bins. Okay? So here we have 6 bins on the y dimension, 1, 2, 3, 4, 5, 6. We can also divide the x-axis to 6 bins. So now we have 36 blocks. And if the predicted XY location fall into the correct bin, then that's a correct prediction. Okay, so that's converting the continuous value into a discrete value. Once it's a discrete value, we can use the cross entropy loss to cast it into a classification problem. Like here we have 36 classes, right? And for X we have 6 classes. 1, 2, 3, 4, 5, 6. And here the ground truth should be the second class. And so that we can use the same cross entropy loss to supervise this detection problem for discrete locations. Now we try to match the distribution of the class. So the class is basically the location bin, right? The location bin. Y-axis, this is bin 1, bin 2, 3, 4, 5, 6 is a classification problem. How about semantic segmentation? So segmentation is a new task. We try to find, to give a label for each pixel, okay? Pixel-wise prediction. Pixel-wise prediction. Again, we can have the same feature limitation similar to classification and detection, okay? What is new here, we can add a discriminator network to provide the adversarial loss, okay? The student is trained to fool the discriminator network. So we have a real embedding from the teacher model, give a real embedding. The student net give the fake embedding, okay? And here we try to fool the discriminator cannot distinguish between the real embedding versus the fake embedding. And we can also try to encourage both the teacher and the student to grow to be as accurate as the teacher, such that the discriminator cannot tell this is fake embedding, this is from the student. They are thinking these two are as good as each other, and they cannot distinguish them from each other. Then the output given by the student should be very close to the teacher. So that's the adversarial loss as the distillation. We can also use this distillation loss to compress GAN models. I use knowledge distillation for GAN model. In this work we did a couple of years ago, 4 years ago actually, called GAN compression. So we have 2 models. Here we have a teacher model, here we have a student model. First, we can apply the distillation loss to these intermediate feature maps. You can see the teacher have larger number of channels. The student have smaller amount of channels. Here we use a one-by-one convolution to match the channel dimension. Okay? To match the channel dimension. And next we have this reconstruction loss. Reconstruction loss to make sure even the student pixel-wise, to give the pixel-wise, measure the pixel-wise difference with the ground truth, And finally, the third term is the gap loss. Okay, C for condition gap loss. We want to make sure the teacher and the student are close enough so that I can fool the discriminator, telling that these two are basically both of them are real. And the training objective, we add these three loss terms all together to supervise that, so that this small student model can perform as good as the large teacher model. So here we have a demo after compression using GAN compression. On the top is the original cycle GAN, which turns a horse into a zebra. Okay? Unfortunately, it runs very slowly. This is deployed on Jetson Xavier GPU, a very small mobile GPU. And you can see it's very slow. Flops is taking 56 gigaops, only running at 12 frames per second. FID is 61.5. But after GAN compression, the flops reduced to only 3.5 gigaops. That's 16 times lower flops. And the frames per second increased to 40. And FID also increased to 53. FID decreased to 53. Originally it was 61. Here is another demo, interactive demo, edges to shoes. You just draw these edges, and then we want to convert it into shoes. Now we want to erase the logo. We'll try to change from Adidas to a Nike shoe and see how that works. Originally it was pretty slow. This is running on even smaller Jetson Nano. Okay, Jetson Nano. And previously it's running only 1.6 frames per second. And you can see the drawing is very difficult because it's not interactive. It runs too slowly on this edge device. Since the frame rate is so low, it can only sparsely sample a few samples. And barely looks like a Nike shoe. But what if we apply GAN compression to run the smaller model? The erase becomes much smoother. On the right hand side is the GAN compression, the left hand side is the baseline. Now we try to draw another Nike shoe. Now it can run 3.9 frames per second. Okay, it's much smoother. On same hardware, the speed up is about 2.5x, which is quite good. Everything is deployed locally on this Jetson Nano GPU. So we have a bunch of them. If you are interested in this project, feel free to talk to us. We can lend you a few such mobile GPUs. Okay, so we talk about vision tasks, distillation for image detection, image segmentation, for image generation. Let's now talk about KD, knowledge distillation for natural language. Okay. So in natural language, we are going to cover that later. The attention is a very important building block. And we have a projection for QKV, attention, and then output projection, feed forward, and top of layer norms. So what we can try to match is not only the feature map, but also the attention map, okay, which is of open square. So this is showing matching the attention map. What does it look like? So this is the teacher, the first row. The attention map is always square because it's all n by n, number of token times number of token. And this is the student with attention transfer versus without attention transfer. With attention transfer, the attention map is very similar versus without, very different. These two are very similar versus this is quite different. Okay, so in addition to feature imitation, the transformer architecture will give us another opportunity to try to match the attention maps. And knowledge distillation for large language model and also visual language models. Okay, so pruning and distillation can work together, showing this work, okay, to obtain much smaller large language models. So here is the cost to train the model measured in trillion tokens. For example, Llama 3 here they use 15 trillion tokens. This Llama 7B 2.5 tokens. And here we can reduce the number of trillion tokens by a large margin while maintaining the accuracy compared with training from scratch, the Limotron 3 8B. We can have 40 times cheaper, 90% better accuracy on the MLU score. And here is how the whole process works. So it contains, on the left-hand side, it contains the pre-training data mix versus synthetic data mix. So to train both a pre-training model versus an instructor model. Okay? This is instruction tuning. This is without instruction tuning, using the logics coming from Llama 3 8B and also Llama 3 7B. Okay? To distill a model which is 1B, okay, a 1B model. And the instruction tuning data comes from you have some synthetic, you generate some prompt and pass it through the Llama 3 400 billion parameter Llama 3 to get some synthetic data. You concatenate that with some collected fine-tuning data altogether and train this instructor model. Okay, so that's the overall pipeline. And how do we select the student model? We select, actually, this work select the student model using the pruning technique we talked about previously, using to rank those important channels. Okay, so this is the work where Minitron applied knowledge distillation, retraining after pruning the model. Okay, the student model is a pruned version of the teacher model. Okay, so initially we have a pre-trained large language model, many layers, and then Minitron basically going to estimate the importance of the embedding 1, 2, 3, 4, head 1, 2, 3, 4, and etc. And then it's going to rank them according to the importance, and then prune away those less important channels, tokens, heads, etc. And then distill it using this as a student and the original LLM as a teacher to distill them. And here it can match a lot of different tensors, okay, the embedding, NLP, etc. The distillation not only matching the output logics, but also is trying to match those intermediate features. Okay, so we talk about distillation for different tasks, for both region tasks and also NLP tasks. And finally, let's talk about network augmentation, another piece of work very related with the thought. So we try to improve the accuracy, the quality of a small model. Okay, that's the central topic of this lecture. How do we improve the accuracy of small model? Data augmentation is a very widely used in training to avoid overfitting. For example, if we have a limited amount of data, we want to augment it such that we can, as if we have a larger amount of data. Small amount of data versus larger amount of data. So typical way of doing data augmentation for vision tasks, including cut out. For example, we cut part of the image, okay, and human can still tell this is a dog. And also we can mix up. For example, we are given an image, a cat and a dog. The cat given label 1, 0. The first one is cat, the second one is dog. So cat has a label 1, 0, dog has a label 0, 1. We can mix them up half and half, just pixel-wise add them up, and then the logic would be 0.5 and 0.5. So originally we have only 2 images, now we have a third image. So let's mix up. Also there is work called auto-augment, where we can tilt it, or we can tint it with different colors. We have a lot of different policies, both spatially and also in the color domain. That's called We can also use AutoML to automatically find the best augmentation policy. Apart from data augmentation, another way to prevent overfitting is using dropout. So during training, we randomly select a few neurons and zero them out to drop them out. Also, people can do spatial dropout to randomly remove a few channels, and also drop block to remove a few blocks in the coarse granularity. As a result, these techniques like dropout, like data augmentation, can greatly improve these large neural networks' performance. Here is the performance of Resident 50 as 4 gigamax. And this is image net top line accuracy. This is the baseline of about 76.5. This is after mix up, almost 78. This is after auto augment, more than 77. By using drop log, it's more than 78. Okay? So for these large models, dropout and data augmentation really helps because large models tend to overfit. So dropout and data augmentation prevents overfitting. However, for tiny models, we did the same experiment. Unfortunately, both dropout and data augmentation actually hurt the accuracy. Okay? So the more we add, the more techniques we add, the less the accuracy. Okay? So adding mix up, it hurt. Adding auto augment, it hurt. Adding drop block, it hurt. And previously, when it helps most, now it hurts the most. And we suspect the tiny model lacks the capacity, doesn't suffer from the overfitting issue, but suffer from the underfitting issue. We don't have enough capacity to learn so much knowledge for the tiny network. So contrary to image augmentation, now we think about, can we do network augmentation? Okay? To augment the model to get some extra supervision during training for the tiny model. So in the end, we still want to deploy a small tiny model. Like here, we use 2 channels rather than 4 channels. But during the learning process, we find some redundancy helps. If you can sometimes have 4 channels, sometimes 3 channels, not just these 2 channels, it is helpful. For example, once you get stuck in the local minimum, some extra dimension, some extra degree of freedom can help you get away from the local minimum. And indeed, network augmentation for the tiny model, this is more than V2 tiny with only 23 minimax. Here we have 4 gigamax. Okay, so 2 orders of magnitude difference. After adding that on, the accuracy finally improved. So how that works? So this is the vanilla training. We have a very small model with only two neurons, in this case 3 layers, 2 neurons. And then we build an augmented model out of this original model, very similar to the once-for-all network. So here we start with a small model and then expand it in different dimensions. Okay, we can use child dimension, we can use the depth dimension, etc. We build an augmented model. Okay, and similar that principle can apply similarly to large language models by increasing the number of paths or increasing the number of channels, etc. Build an augmented model, and we concatenate the base model with the augmented weights. W base, they are actually shared for the red part here versus the red part here. And then we get a gradient both from the G base, gradient base, versus the gradient from the augmented model. Okay? And we are going to add them up all together. So this is the base supervision, this is the auxiliary supervision. We add some extra supervision to the base model. A different step, we can sample different size of the network. Sometimes we sample a larger model, sometimes we sample a smaller model. What doesn't change is the inner part. They all share the same weight with the original small model. And as a result, we can see the learning curve for both. Here is the training, here is the accuracy for validation. That all improve the accuracy both in the training time and also the validation time. And both on the training and also the validation for the tiny model. Okay? But for the large model, it actually didn't help, but hurt the accuracy. Okay? So for the training, it indeed helped, but for the validation, it didn't help. Meaning that the large model already has a pretty big capacity, doesn't suffer from underfitting but overfitting. What they should do is to augment the data, not augment the model, which is actually echoing with our previous assumption that these large models are overfitting and small models are underfitting. Here we are showing network augmentation is actually orthogonal to knowledge distillation. So not far in the baseline, this is knowledge distillation, red one is network augmentation, and this is network augmentation plus knowledge distillation working together. And also for transfer learning, we compare two scenarios. One is knowledge distillation, and then another one is just training longer, training for 4x longer. Sometimes the accuracy hurts using these techniques, but using natural augmentation, it provides a better transfer learning performance than knowledge distillation and also than 4x training schedule. So we also try to apply natural augmentation to object detection. Okay, so not only classification but also other tasks. This is the baseline. The x-axis is the number of maps, how much compute you have. Y-axis is the classical VOC accuracy. Here is the total accuracy. Okay, so for the same model, we can improve the accuracy, and equally we can reduce the MAC if we want to achieve the same amount of accuracy. So this is the limitation here is that it only explored these vision tasks. It was this work was done early 2022, actually submitted 2021 before these ChatGPT came. So it might be very interesting to try such ideas, natural augmentation to train those small large language models. Welcome to talk to me if you're interested in that for the final product. All right, so let's have a summary of today's lecture. We shifted to a new chapter about small model. Okay, apart from pruning, quantization, now we are talking about knowledge distillation. We need a teacher and a student. Okay? We can match several components. We can match the final output. We can match the intermediate feature map. We can match the intermediate weight. We can also match the intermediate gradient. Not necessarily do we need a teacher model. We can also do self-distillation and online distillation so that we can train only once and distill during this training process. Such knowledge distillation can work for many different tasks, not just classification, but also we talk about how to apply that to detection, to segmentation, to GANs, to natural language processing. And also we talk about natural augmentation, an orthogonal technique to improve the accuracy by augmenting the model. So in the next lecture, we'll introduce the MCUNet, which is algorithm system co-design for TinyML so that we can deploy them on microcontrollers. All right, that's all for today's lecture. Thank you.